know when everybody says anything now, but when I get like talking about something that kind of is off the cuff, I always forget. So thanks for reminding
No
me.
problem. And I had another question real quick
Okay.
before you start. For the final exam, because some of my classes are giving us an option, you know how like say if you already have a good grade, it's an option to take this
Well,
class.
unfortunately, math doesn't do that.
Okay.
So
All right. That's fine. I'm
because,
just
like I
curious.
said, they're departmental, those exams. What kind of class is it that does that? What department does that?
I think psychology.
Yeah, and that makes sense. But like I said, the
It's fine. It's no
math
big
is
deal. All right.
math is just there's so many darn departmental rules now. We've been doing that for years, going towards that direction. We don't have a whole lot of control over, you know, those kind of things. Because I remember I specifically asked about that because when I first started teaching, people would say I would get a hard test. So I remember asking, I said, well, people, have an A going in with to the final. Can I exempt them from? And the department lady said, "Oh no, you can't do that." But you know, that's not changed since. I wish it would, but all right. So what we're looking at is chapter 10, section 10.7, 10.8, and these things deal with or and probability. These are what we call compound rules. And if you remember back in chapter 2 and chapter 3, or related to the union of two sets, and related to the intersection. And as a matter of fact, in chapter 3, you use or and to make compound statements. And that's what these are here. These are compound probabilities. And they're really pretty easy. It's just you got to remember, if you got an or in your problem you're working out, you're going to have to use the or rule. And this is really the main and only or rule there is, although I'll show you something kind of peculiar about it because you'll see the two graphs there. But notice that the probability of A or B happen, in other words, one or the other things, is the probability of A plus the probability of B minus the probability of A and B. Now that should look familiar because that's also the way to calculate the number of elements in the union of two sets. And there's two scenarios. If the sets are mutually exclusive, then there's not going to be anything in that A and B. But if they're mutually exclusive, you're counting some things twice. And as you remember, we did that exact same thing, except for a P there. It was an N for the count. So that formula is exactly the same, except now we're doing it with the probability. And the probability is really not much different. So remember, mutually exclusive means that they have nothing in common. And mutually exclusive means that they have overlapping elements. Now, if we're in this situation here, in the first situation, mutually exclusive, then this collapses here, the probability of A into B into 0, and you got this probability of A and probability of B. You don't have to worry about subtracting them out. All right. I'm going to take these out and rework them. All right. And what I'm going to do here is I'm going to put this one first. Because what we're looking at now, we're looking at, I want the first problem to be one where they're mutually exclusive. All right. And this one is easy to see that it's mutually exclusive. So to find the probability of picking a club or a red card, obviously there are no cards in there that are both red. Since club is black, there's no cards in there that are both red and a club. So the probability of club or red is equal to, well, first of all, how many clubs are there? There are 13 over 52. Well, let me go through the full thing. So this is going to be the probability of club plus the probability of red minus the probability of club and red, if there are any. I'm just putting it there just to show you that it fits the formula. So now, this is equal to the probability of club, as I said before, was 13 over 52. And then the red ones, well, that's half the deck. That's 26 because you got 13 diamonds and 13 hearts. And now, are there any that are both club and red? Well, no, they are. You don't have to put the 0, but I'm just putting it there to show you that that there are none. Because sometimes it might be better to just always use the big formula, and then just check as you go. So this is 39. Oops. All right. So the probability of picking a red, a club, or a red card is going to be 3/4. And you can kind of look at it proportionally. 3/4 of the deck are either a club or a red, and there's none of those things in common. Okay? Questions?
Is it 0 only because there's none of those things in common, or would that 0 ever change? Okay.
Yeah. It will change in this case right here to the extreme right here. If they're mutually exclusive, then there's going to be a probability in there, and we'll look at that. We'll look at another mutually exclusive, and then we'll look at one where it won't be 0. Now this one's a little bit harder to see, but we're talking about doing two different things, one or the other. When we're talking about or, you're not going to do both. You're going to do one or the other. So what's the probability of rolling a 6 on a die or flipping a coin to get ahead? Because if you did both of these, you could come up with a 6 in theory and get ahead. But we're talking about doing one or the other. So again, it's or. So it's just the same formula. You can't have both, so that's going to be 0 as well. And then the next time I'm going to show you the one where we got ones that aren't mutually exclusive. So this is 1/6. This is 1/2, and then that's 0 again. So 1/6 plus 3/6 is 4/6, which is 2/3. You always, whittle your fractions down. If it asks you to round off, ask you to approximate out to a decimal place. In the case of like 3/4, that's going to be 0.75. It'll go out to 2 decimal places, regardless. You don't have to round it off. But on 2/3, that's a repeating decimal, 0.66666. So you'd have to be told where to round it off at. All right. Now, here we go. What is the probability of selecting a red card from a deck of 52 or picking an ace? So you're going to go in there and do one or the other of these things. And because there are red aces in there, then you can get both of these on one selection. All right? You can have an and on one selection. So that's the original formula. And this is not going to be 0, as we'll see. And the reason why I'm taking you through that with the zeros like that is because I really think that generally in math, there's, too many formulas handed out there and people think that they have to remember. So with this, there's really just that one formula. It's just add them up, take out any common ones. If there are no common ones, then you don't have to worry about it. All right, so the probability of red, well, half the deck is red, right? 26, because there's two suits of 13, so there's 26. Now, how many aces are there? There are 4 aces. There's 2 black ones and 2 red ones, but I'm going to put both of them. But here's the thing. These are not mutually exclusive. I mean, these are not mutually exclusive. So we've essentially counted something twice there, because the 26 over 52 includes 2 red aces. All right. So if we were to add that up, we would come out with 30 over 26, not 26, 52. So what we got to do, just like we did in chapter 2, when you were counting the number of elements in the union, you got to subtract out those that repeat. And there are exactly 2 out of the 52 that are both red and an ace. Does that make sense? So say
Yes.
This is not 0 now.
Out of random curiosity, will you always be given the additional number? Like if I had never ever played with a deck of cards before, which is not the case.
Well, but I've showed you that on several occasions, and we can go back to it. Usually,
no, I know.
They will show you a picture at some point.
Will you always be given the overlap, is what I'm asking? Or is that
ever
going to be?
Okay. You're going to be showing some kind of a picture, like the sample space. We looked at that when we talked about sample spaces.
That's all I need to know.
If it's a pinochle deck, I'd have trouble visualizing that. I know, because it's different. So yeah, they'd have to show you that sample space if they're asking you about something that's not, like not seeing. And the reason why I put the sample space for the cards in there when we were talking about it is because I know there's always people that grew up not playing cards. I mean, my wife, they couldn't play cards. So, I had to, deal with that and have to show her, kind of thing. So that's why I always assume it here. Because there's always somebody that tells me.
I was just making sure that we were always going to get that number. That's all. That's
all.
Well,
the saying is, if you want to see how it works, then we go back to the sample space. Where was it at? I had it in here twice.
You can just keep going forward.
What I'm saying is, I had it in here a couple of times, but see, for people that don't know, and that's a good question, see, there's your 4 aces, here's your reds, and they intersect. So you remember we talked about intersection in chapter 3? Well, chapter 2. Well, there's your intersection. You got the 2 reds, aces, that are both. So it's a good question, Kevin, because there's probably somebody that didn't want to ask. But that's what I said is, you're going to have to, they're going to give you some description of it, They can't just throw a situation out there. All right. So now let's talk about the and rule. Let me finish this. So that's 28 over 52, which is 7 over 13. Because both of those are divisible by 4. All right. Danielle, gotcha. Let's see. But like the ones in Alex, they usually give you some kind of visual. I don't remember there ever being anything that it didn't give you a visual for in there. So. All right, so let's talk about the AND rule. Well, AND, remember, relates to intersection. And what AND is essentially both of these things happening. Two things happening. Well, it's pretty simple. That's the rule for AND. If you want to find the probability of this and that happening, then you're going to multiply. Now, I want you to think about this. When we were talking about OR, we're talking about one or the other things happening. So it ends up being, when you add two fractions, you get a larger fraction. And that's what happened when we're talking about OR. Now with AND, you're talking about two things happening. And remember, probabilities are always a fraction. So if you multiply one fraction times another, you get a smaller fraction. And hopefully that should make sense, because if you wanted to say, what's the problem of me making a bet on a horse and winning the lottery? Well, if you want both of those things going to happen, you're multiplying your probabilities, and it's less likely that both would happen. But if you said one or the other, still going to be kind of remote as a probability, but it's not going to be as remote if we talk about and both things happening. And can be extended out to more than one thing happening. And then every time that happens, you're going to end up with a smaller fraction, because you're always multiplying a fraction times a fraction when you're multiplying probabilities for AND. All right. Now, let's just kind of back up. As with the OR rule with the OR and adding, we had mutually exclusive and non-mutually exclusive. Well, here, it's very similar. You've got things that are independent events, and then we'll talk about dependent events in a second. But right now, let's just focus on independent events. In an independent event, if we're talking about two things happening, independent events are things that don't affect, or the first iteration or the first roll of the die does not affect the second one. And that's what I've got on in the first example. So if they're independent, then you just calculate the two probabilities and you multiply them. And you always do that for multiplication for AND. It's just that we'll see about dependent events in a minute. All right, so we got, suppose we roll a dice twice, then what is the probability of getting a 6 and a 3? All right. Now, these are independent, and think about this, because if you take a die and roll it, and let's say you get your 6, the next time you roll it, you're still going to have the same probability of getting a 3. All right. Still 1 out of 6 on there. The probabilities don't change. Or you could even think of it like this. Let's say we were asking about rolling 2 6s. Well, you roll 1 6, you got it. And then the next time you roll it, you've got the same probability. All right. That's what we mean by independent events. They don't affect, or the second one isn't affected by the first, is more likely, the more obvious situation here. Because the first one is always fresh and not affected by anything. All right. Suppose we roll a dice twice, then what is the probability of getting a 6 and a 3? So the probability of 6 and 3. All right. There's nothing to add or subtract here. It works slightly different when we talk about dependent events. You're still going to multiply. So I'll just kind of show you one little thing that makes it that it's a matter of notation for the second one when they're dependent. We'll see that in a minute. So both of these are 1 over 6. And what this amounts to, you remember we looked at the sample space for like 2 die, 6 times 6. So you got 30 different outcomes. So it's the same kind of thing here. You're dealing with 2 die, so there's 36 different things that could happen. So 1 over 36. I might have probably should have put this second one first because these are surely independent, because what happens on that die certainly doesn't affect flipping a coin. But again, they're independent nonetheless. So again, there's 1/6 probability there. And then on the flipping the coin, there's 2 sides, so it's 1/2 for the tail. Multiply them. So remember, when you multiply fractions, you got to remember about that. You're multiplying the numerators times the numerators, denominators times the denominators. So that's why the numerator is still 1. And then 6 times 2 is 12. And then again, you always simplify it if you can. All right, questions? I'm going to just kind of show you. I think that they do this in the book. And like I said, different books have different things. Let's just rewrite this, and I'll explain what it means. I like to use a little slant in here, but all right. So you'll notice that the only difference between this one and this one is just that I fiddled with that second probability, and I've put B slash A in there. Well, what that little slash means is simply this. It's read as this. Let's say it means and here's the key word for conditional probability or dependent, given that A has occurred. So that's what that little thing means there. There's not anything you really have to do. It doesn't mean division or anything like that. But let me explain to what it means within context. And think back to those cards that we just looked at, that sample space. There's 52 cards in there. So let's say I go up to one person here, like Danielle, I see there, and I say, pick a card out of this deck, and you pick it and hold on to it. So I'm going to do a magic trick, let's say. Now, that first time that deck is pulled out, or the first time that card is pulled out, there's 52 cards in there. So any probabilities that I want to calculate would have 52 in the denominator. All right. Next time I go up to Abed and I got the same deck with that card, one card missing, and he's going to pull, and we're going to calculate a probability from it. There's one important difference now when we're dealing with that deck of cards. There's now 51 in there, so any probability we're going to calculate for a specific card would have 51 in the denominator. Well, this is what we call dependent events. Now, we can fix this and make it like independent events if we want to, but we don't necessarily have to. But I'm just trying to explain the difference here. So let's just say if you were to take the deck, let somebody pick, write down what their card was, put the deck card back in, and we shuffle again, and then we let somebody else pick, then it's going to be independent. So sometimes when you see that word with replacement, that means independent automatically. But if it says without replacement, or specifically says without replacement, and they may not have to tell you that, you know, it just may be in the context that somebody keeps the card, it's obvious that it's not replaced, then you know that that first pick affects the second one. All right, so let's look at how that goes. All right. I see I put in there without replacement because that's important. What is the probability of picking both a jack and an ace without replacement? In other words, I'm going to go up, let somebody pull it out, and we got to assume that the first card picked is a jack for this to work. So that's 4 out of 52. And I'm going to put that little slash, and so I'm going to put given that the first card was a jack. Because we got to assume that we got it, that the first person gets it, or there's no sense to doing the second pick. So that's why, like I said, that's the importance of putting that little slash. Does it mean that the first event happened and it affects the second one? So on the first pick, there's exactly 4 out of 52 that are jacks. Now, we're going to multiply it times the probability of the ace. Now, if we had done 2, and we're going to see this in the second one, but there's now 3 aces in the deck. I'm sorry, 3 jacks in the deck, and there's still 4 aces out there, but there's only 51 cards now. So we still got 4 in the numerator, but the denominator changes. And as we're going to see in that next example, it is possible for both numerator and denominator to change depending on what the first pick is. So this ends up being, I'm just going to put, because it was a pain in the neck to do that before. I'm just going to paste this up there. Because like I said, is when you multiply probabilities, the numbers are going to get big real quick in the denominator, which ends up being a smaller probability. So 4 times 4 is 16. 52 times 51 is 2652. If just to kind of save a little bit of time there, we're going to just round it off the 3 decimal places. So that's tenths, hundredths, thousandths. So to do both of those things, the probability would be 6/1000. And like I said, is you pay attention to what they want you to round it off to. If they say fraction in simplified form, then you could probably whittle this down a little bit. What would it be? I'm gonna go ahead and do that just so I can play good teacher here for both, because it is a possibility they want to have both. I'm gonna use my calculator here.
I was writing. I wasn't sure if I missed something. Is the negation mark supposed to be there?
Was there a negation at?
Right
Oh, that's
before the
well, okay. On a keyboard, you can't really
equal sign?
do two squiggles. I'll show you something. It's not a negative sign. This right here, does anybody know what this means here? You'll see this. And I can't really, there's no way to put that in on keyboard. So what I do is I do this. Put the little squiggle and then put equal to. So what that means is approximately. So once you show that, that means that we've approximated. Because if you type in okay, because if you take that fraction, what was it? It was 16 over 2652. Hold on a second. No, it was 16 over 2652. So you could go down to 4,663. Because they're both divisible by 4.
I think you're still screen sharing the wrong screen again.
Oh, sorry. So I'm trying to do this to just give you both. I was trying to be a little bit lazy there, but I'm going to go ahead and put this in. All right, so when you multiply it, it comes out to 16 over 2652. Both of the numerator and denominator are divisible by 4, so we could bring it down to 4 over 663. But you got to just watch out. Sometimes they say approximate, okay? Approximate out to such and such. Well, if we approximate this one out to the first decimal place that it has a number, which is the thousandths, then it would be approximately 6,000. Because if you take, let me see something. Let me just show you this. I got this calculator. This is not the one you use, but it'll work for this demonstration. And this is why, and the people in Math 203 have fits with this, because this calculator and any calculator, once it gets past a certain number of decimal places, it's going to put it in scientific notation. So it was 4 divided by 663. Well, this one doesn't. So that's rounded off. See, it keeps on going. It repeats. So the only choice we have, if we're going to write it as a decimal, is to approximate it. So that's why I got the squiggle. And like I said, it's a typing squiggle because there's no double squiggle on the keyboard. Now, I don't think y'all have to worry about this. I'm not 100% sure, but let's just say if we did 5, whoops. I don't think y'all have to worry about it, but this is just something like that. See that? Does anybody know what that means? This is what they run into in Math 203 because they think the calculator is going to solve all the problems, and it doesn't. So this is just a little mystery for if you've taken Math 203. All calculators do that. Once you get past a certain point of it being small or large, they use scientific notation, and that scientific notation, that -5 means, well, the E means that it's scientific notation. The -5 means we got to go 5 decimal places to the negative sign. I don't think y'all have to worry about that, but I thought I'd mention that because it was on my head.
I always thought it meant enough is enough.
Well, yeah, it does. I mean, but like I said, the problem being is we get to use calculator, real fancy calculator in Math 203, but it doesn't solve all your problems because, whoa, what does that mean? All right. So let's look at another one that's where we got dependent events. We got a class of 10 students, and in there you got 6 humans and 4 lifelike robots. Now, we're going to pull 2 students out there to send them somewhere. But we want them both to be robots. So, what is the probability if we pick 2 that both are robots? Well, this is the way it goes. We want probability of two robots, which is the same thing as saying robot and robot. Though, sometimes you're going to get it like that where it'll just say 2, but that's what it means. Okay? Well, it's equal to the probability of a robot times the probability of getting a second robot given that the first one was a robot. So what's the probability of on the first pick that we get a robot? Well, there's 4 in there. And then there's 10 total. All right. Now, here's where we're going to affect both numerator and denominator on our conditional pick. I mean, that first pick is affecting the second one because we no longer have 10 students to pick from. We got 9. And since it's important that we have 2 robots, then we got to assume that one was picked on the first try. So there's no longer 4, but there's 3. All right. Does that make sense? That's conditional. That's a dependent event. All right. This right here is what this is represented by that in this situation. That 3/9 is the probability of picking a robot given that one has already been picked. So that's 12 over 90, which is my brain's not working too well today, but I'm going to get it for you. So that's 2/15. And then what is 2/15 if you wanted to approximate it? I think this is maybe this is that's a repeating decimal. So I'm going to do this again just so. And I can't put a bar over it, but imagine a bar over that 3/3. But let's just say we wanted to go out to the 3rd decimal place, then that would be rounded off. Take your calculator and do 2/15, and you can see what's going to happen. Because in some cases, you just have to round off, and it's considered an approximation. So that's why I got that little squiggle thing there. The 1 doesn't repeat, but the 3 does. All right. So we're almost finished here. All right. Complement rule. Remember that? That was where, the probability of an event occurring plus the probability of it not occurring have to add up to 1. So that if you want to find the probability of rain, if you know the probability of rain today is 70%, then the probability of not rain is, well, you subtract that from 1 or 100 if it's in percent. So 30% would be the chance of no rain. They have to add up to 1 or 100% if you're using percents. So we can also use that.
Mr. Cruz, this thing keeps kicking me out. Is it you or is it my phone?
Is anybody else getting kicked out? Are you on a phone or are you on a?
I'm on my phone because I'm at court.
Well, I tell you, I can't. I'm surprised you can do anything on a phone. The last time I tried to attend a conference on the phone, I couldn't do anything. So you got my sympathies there. I don't know what to tell you about that. I tried to do something on the phone. It was like.
I understand, but I'm at court. I can't. I have other stuff to do too.
Yeah.
So that's what I'm saying. It keeps.
I'm just saying, just keep getting in. I mean, the only thing, and this does work. This works to a certain extent with a phone too. But if you reboot a computer, usually that fixes a lot. So I remember one time my daughter was talking about her phone that she doesn't get all of her messages. I said, "Why don't you just try rebooting it?" And she, turned her phone off and turned it back on, and then all of her text messages came in. So try that, because computer-wise, that usually fixes a lot of things. All right. So this is what I like to call the complement rule revisited, because if we want to find the probability of an event occurring at least once, we can find that by using the complement rule and subtracting the probability that an event does not happen from 1. And oftentimes that's quicker than just doing this part. And I'll kind of show you what I mean here. All right, so let's find the probability of flipping a coin twice and getting at least 1 head. All right, at least 1 head. So that means then, and this is a sample space here for 2 flips. You got head, 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 tail, tail, head, or tail, tail. Now, in this very simple case, it's easy to see that there's 3 of them that have at least 1 head in there. The only one that doesn't have a head, no heads, is that one. Well, like I said, you can use the complement rule. In this example, is to make that easy to see. The probability of at least 1 head is 1 minus the probability of no heads. So you have less counting to do this way. So 1 minus 1 out of the 4 is 3/4. So there's 3 over 4, as we can see, and 1 over 4 that have no heads. And like I said, oftentimes that's easier to do that. So let's try it. With 3. Well, if you think about this, if you flip 3 times, that means tail, tail, tail. All right. Well, there's only one way that can occur. And if you remember your rule from back in chapter 2, where we were talking about the number of subsets, well, that applies here. So we know there are going to be 8 different subsets. It also applies to the counting rule. 2 times 2 times 2. So there's 8 different outcomes. So it's a little bit easier like that oftentimes than going through and counting how many directly. All right, where's my water at? Forgot to bring it over here. All right, so last thing is, this is related to that dependent events thing, but I wanted to handle it separately because it can be a little bit confusing. And usually the way this works when you're dealing with conditional probability, you're usually dealing with some kind of a chart. So let's just look at this. Now this is that same thing I was telling you about over there. In general, the probability of B occurring given that A will occur is called conditional probability. Is written as probability of B given that A has occurred. All right. All right, well, let's just look at this here. This is the easiest way to look at it and see it visually. All right. So we got some data here, and it's in columns and rows. And what it is, it's the number of times students visited the tutoring lab like we got. There's one at City Park. I mean, since I'm based out of the West Bank, we've got one over there that's smaller. And, you know, they keep track of people going in and out. This is not from there, but it's the same idea. All right, so they tell us on the columns, it says that they've been visited one or fewer times. So somebody just shows up and then never comes back. 2 or 3 times, so they come 2 or 3 times during the semester, and then there's a group of 4 or more times. All right, now down at the bottom on the total, you can see they're adding up. So 12 and 2 is 14, 25 and 5 is 30, 8 and 6 is 14. So they're totaling the 2 rows because the 2 rows are broken now into full-time students and part-time students. And they also break it down that way as well, okay? All right, so let's see what we can do here. I'm gonna try to put something in here. Let me put in just a regular one first. All right, so if we just deal with a basic probability, watch how it works. I'm going to just kind of show you the distinction between this and the conditional probability. All right, so if we just find in regular probability, there's no stipulation in here. It just says find the probability that a part-time student visited the lab. All right, so probability of part-time. Well, we're just going to go to the total of 58. And then we're going to go to the total of part-time visits, which is 13. And so there we got our probability. And there's no way to reduce that. I'm just going to leave it as a fraction. So that's basic probability. But notice this one has this funny word in here. Given. All right. Now, that first one did not have any stipulation other than just part-time. But this has kind of 2 things. It says 4 or more times, given they were full-time. So therefore, what follows that word given is what we're going to look at as our total. All right? Not the 58. We're going to look at full-time students only. So what's the total of full-time students? Y'all look at that.
$45 out of 58.
Okay, you can look at it like that, but I just wanted the total. And you can do it like that way. It's just longer. I see what you're saying. But we're going to just do it the easy way. So how many are full-time? Well, it's just 45 now that we're looking at. All right. So given means we're now changing what set of students we're looking at. We're not looking at total. We're looking at full-time students because it says given that they were full-time. So it's making two stipulations, and the one that affects the denominator there follows the word given. So we're only looking now at that first row of students. So we're taking that total and we're putting it in the denominator there. All right, now, how many of those in the first row went 4 or more times?
8.
8, good. Let's see if I can find something real quick. And because you thought about it, right, Kevin? I just it's easier for this class. There's somewhere that this thing is mentioned, and I was going to try to find it. Let's see. As a matter of fact, hold on a second. Okay, this is the official formula for this. And so you could have, Catherine, you could have put 45 over 58 in the denominator. And then for the numerator, you would have been put 13 over 58. So let me just kind of, I'm sorry, it wasn't 13. What was it? It was, yeah, 14 over 58. So let me just show you on the board. So like I said, I'm trying to kind of show you a quick way to do it. You can just do it with the counts rather than the probabilities, and I'll show you why. So it was 4 given full-time. All right, so then let me type it out. Well, put the line. And then up here, you put the probability of both 4 and full-time. And so what we could have done, so it was 45 over 58, right? I'm going from memory, so beat me in the head if I got that right. And then the numerator, it was 8 over 14. It was 8 because it was full time. Hold on a second. No, I'm sorry. It was 14 over 58 because it was a total. Well, this is what we call a complex fraction. And so what does that mean? Well, it means 14 over 58. And now if you remember, the when you've got a fraction, that essentially means division. So it means 14 over 58 divided by 45 over 58. Like I said, that's why I didn't want to take you through this, because I just wanted to show you the quick way. But if you figure this out,
way.
yeah. So now it's 14 over 58. And how do you divide? Well, you multiply by the reciprocal. And what happens? Well, notice that these two are 1, and so you're left with 14 over 45. So what does that mean? Well, let's see if I can write this and then drop it in the thing. Let's see if I can do this real quick. I only got one other problem I want to show you. So but I can put this, I want to drop this, create this nice, and then put so instead of doing the whole probabilities, what was wrong with me? I had too much caffeine, I think. So you can do this, and some books will mention it, some won't. But I wanted to show you this because it's a lot easier to do it this way. Remember that little symbol, what n means? It means the number of elements. All right, so let me copy and put that over there in the notes. Because I've been trying to find one of these, and I've got it in my statistics class notes, but it's not something that people use a lot. Or use this, which is what I did here. The 8 over 45, it was all that's left. So we were looking at full-time students because that was the given. So that becomes the denominator. We're only looking at that one row. And then we look at the intersection of 4 and full-time, which gives us the 8. Hold on a second. I messed that thing up. Let me go back and fix it. This is what happens when I do stuff off the cuff. Hold on a second. Where did I make the mistake over here? All right. Let me come back to that. I did something that's messed it up. I'll fix it in a bit. I just want to make sure I get to this last thing. Believe me, it works. And this is what I'm showing you right here. I just messed it up on the board. Whoops. I'm still showing you the board. I did, messed up on the board because I was trying to go off the cuff. The formula's right. So.
Is it just supposed to be an 8 instead of a 14?
Yeah, it is. So this shows you that. And I had done it right when I had done it early, So what you're doing is the given tells you you're looking only at 4 full-time students. So that becomes your denominator. And then in that row, you find the intersection with the other item, which in this case was 4 more times. See, that's a lot simpler than doing that fractions. And like I said, I was trying to look there where I messed up and I couldn't even see it because I wanted to. So let's just do this one real quick and then I'll show you this last one. Find the probability of selecting a full-time student given they visited the tutoring center 4 more times. Now, the given has changed. So I'm just going to do this the short way. Backwards. So now we're only looking at, and I don't have a picture for this one. We're only looking at, and this is probably what I did on that board. I was doing this one. So the given is 14. I'm sorry. So we're now looking at 4 more times, just that one column. So there's only 14 on that. Now, we still find that the intersection of the 2. And so it's 8 over 14 now. Same intersection, but the denominator changes because the changing of the word given. And then that ends up being 4/7. All right, if you got questions, we'll come back to that. Like I said, I know I messed it up. But let's look at this last one. Because this looks at it as in a different context. Because it doesn't have to be a chart. Usually charts make it a little bit easier to see, and they're often used in these problems. Now, what is the probability that we're going to take this thing and we're going to spin it, but somehow we're going to predetermine the given part? All right. So what is the probability of blue given that the number we select is even? So without even thinking about it, you look at what follows the word given. And what follows the word given is even. How many even numbers are there? What was happening here? I know what it is. My battery is dying here. Hold on a second. This is the kind of thing, of course, happens when Trump is trying to rush. I wanted to finish all this. So next week will be review, but let me just do this last thing. All right. So what follows the word given is even. How many even numbers are? There's 8 numbers here, so half of them are even. Now, out of the, half of them are even. So how many of those are blue? How many of the even ones are blue? These are the only, oops, it's not, yeah. So there's 2 blue ones that are even. So when you see the word given, whatever follows the word given is what you're going to reduce your denominator to, because you're making the condition that you're only looking at that group. So you got to either, when we looked at it up here, it was isolate a row or a column, and then look at only the ones where the intersection occurred. Because that's what I wanted to show you this one, is because you can see it more clearly as an intersection. Whereas with this one, it's harder to see that. But what follows the word given is even. So you're only looking at the blue ones. I'm sorry, the even ones. There's 4 even ones. And now out of those 4 evens, how many are blue? Well, there's 2 of them, the 6 and the 4. The 5 is not even, so we're not looking at it. So then there's 2 out of the 4 or 1/2. And you could do it find hold on a second. Okay, so this is going to be slightly different. So how many of them are blue? Well, there's 3 of them. And how many of those blue ones are odd? Well, there's only 1 of them. So you can turn it around in both cases. You can always turn them around, and when you do that, something different will come out. Now, if we had said even given the number blue, then it would have been 2/3. All right, so have a good weekend. And so there, we got that fixed. So long way, short way.